Okay, we've got to digress and talk about trig substitution. So it seems that nobody covered trig substitution. Let's just say we want to integrate 1 minus x squared with respect to x. Now, you probably have the instinct, let u equal 1 minus x squared. But if you let u equal 1 minus x squared using substitution, you're going to get an x dx when you take the difference. Okay? So du would be x dx. You don't have an x dx, you just have a dx. If it was the integral of x times this, well, let's just do that real quickly, just to contrast it. Okay, so use 1 minus x squared to use 2x dx. So that x dx is du over 2. So what we now have is we have the integral of the square root of u times du over 2. And that's easy to integrate. Okay. And that's going to be now that's take the derivative of u to 3 halves, which is 3 halves u to 1 half. 3 halves of that, it's going to be 2/3 of that. Yeah, 1, right? Okay. There it is. Then I'm not going to details of that. That's very standard, very basic integration, which I probably screwed up, so check it. Yeah, there it is. Okay, now, if we do the square root of 1 minus x squared, well, that's not going to work because we don't have an x dx. Is that equal to any kind of a du, right? So what we do is we let x equal, I'll choose sine theta, it could be cosine theta. And you do that because why? Because 1 minus sine squared theta is cosine of theta. And if that isn't something you've seen 1,000 times, make yourself a note. Look at it 1,000 times before nightfall. Okay? Well, you can't do that. You would be seeing it. Okay, then dx is cosine theta d theta. This becomes the integral square root of 1 minus sine squared of theta times cosine theta d theta. And that becomes the integral cosine squared of theta d theta. And you do that. These are trigonometric identities. Okay? And when you get that, and I'm not going to go through the details because we're real short on time, like we're out of it. But when you get that, then you substitute, well, theta is the inverse sine of x, right? So there are 2 steps that we're using this, but that's where it starts. Another instance, you like we got the square root of 1 plus x squared. Then you let x equal the tangent of theta. Okay. And the derivative of x tangent theta. Secant theta, is that right? It's sine over cosine, okay? So you're going to have cosine over have to record out. Brain just isn't working. Anyway, well, yeah, let's assume that's right. The point then is you have the square root of 1 plus tangent squared theta and the tangent theta, secant theta, d theta. Of course, 1 plus tangent squared is secant squared. Okay. So now you're going to have a tangent times a secant cubed, right? Square of that's going to be a secant. Secant is a reciprocal of cosine. And this comes out sine over cosine of 4 theta d theta. And let u equal cosine theta. So the du equals sine theta d theta. Okay. This becomes the integral of 1 over u to the 4th. du being integrated. Okay. Okay, I got that derivative right in my brain. I've done it for the method substitution of some kind. So my brain doesn't quickly on it. I have to write it out. But you're doing. Sine theta over cosine theta prime, right? The easiest way to do that is closing rule, right? That's going to be a cosine, and that's going to be a negative sign, right? Now you got sine plus cosine over cosine squared. Anyhow, you do it. But these are two main trig substitutions. Okay. If I had a square root of a squared minus x squared, well, you're going to have to do that out. So get a copy of the OpenStax calculus 2 text and go to the section on trigonometric substitution. I think that's what it's at. Okay. You'll recognize it. And with just a little practice, you get that. Okay. Try to get that in the next week or so you can actually do some of these trig substitution come up all the time. In the meantime, when you use your calculator to do the actual integration, it's okay, but come back after you get all the techniques and do the integrations by hand. It's a big deal rule. And already I've written down the base of the exponential. Okay, b to the a equals c. This is an exponential equation in a. So you might want to solve this equation for a. This equation is equivalent to log base b of c equals a. Now there's one other rule that allows you to use your calculator. And remind me to digress. Don't let me finish without telling you how to do powers using those Casio calculators. There's a way to do it. It's a familiar way to anybody that was around. That was a standard way to do it, but that was before y'all were born. Okay, so you got to know how to do that, because the other also need this rule. Log base b of c is just log of c over log of b. Which is also equal to the natural log of c over the natural log of b. And your calculator has buttons for the log log and the ln log. Okay. Now we can use these two rules to solve an exponential equation. So let's do this. Let's take the equation. Two to the 3x minus 5 equals 7. To solve the equation, we look to see if this equation is in one of these forms. Okay. Is equation in the form of a b to the a equals c? I don't think it's in this form. Now I'll give you a hint. It's either in this form or this form, and it doesn't have an log in it. Okay, meaning it's in this form. So the question now is, what's b, what's a, and what's c? I'm going to ask you to write this out on your paper. Tell me that b equals, okay, the form is it's this form. So b equals what? A equals what? C equals what? Now, once you get used to this, pretty easy to solve these equations. So, first step is identify the A, the B, and the C. Okay, you did pretty well on this. Most people got it. There's a little discussion, and everybody doesn't get it. What's the easiest thing to identify? I'd say it's C because it's the only thing on that side of the equal sign, right? Okay. So C would be 7. Okay, what about A? I think that's the next easiest. I don't know, A and B are both pretty easy. But A's up there in the exponent, right? So what's in the exponent? 3x minus 5. And what's B? Well, B is the thing that's raised to the exponent. That's 2. Okay. Now, equation is equivalent to log base b of c equals a. And all I got to do now is write this out, substituting for a, b, and c, right? Just take that expression, substitute your values of a, b, and c that you've identified from this equation, and you have an equation you're going to be able to solve. So go ahead and do that. Let's make sure that everybody's on track. Pretend I don't know what you're doing this, but go ahead and solve this equation for x. If you can, see what you think you ought to do. Let me explain this once more so we have the video and everybody listen here now. Log base b equals c equals a. So you're going to write all this out except we're going to have 2 for b. Let's start that. Log base 2. Because b is 2 of c, c is 7. Equals a is 3x minus 5. Now, I'm not going to show you how to solve this. I want to see what you do, and then I'll show you details. So how do we solve this equation for x, right? X is the unknown. Okay. Aren't you pretty much got this right? Or, really nailed it. Some of you are doing something that you don't want to do, and we'll talk about that, okay? First thing you want to do is add 5 to both sides, right? So you get log base 2 is 7 plus 5 equals 3x, right? Now notice that the 7 still has parentheses around it, right? That's the only thing you're taking log of. You're not going to take the log of that 5. When you add 5 to both sides, you're adding 5 to log base 2 of 7. And log base 2 of 7 is just a number. Now, you don't happen to know what that number is. But it's just a number. So you don't want to change log base 2 of 7. That's just a number. That's a number in itself. We're adding 5 to log base 2 of 7. We're not adding 5 to 7. Okay? It's order of operations. Essentially, this is all in parentheses. And you can't add that 5 inside the parentheses, right? It's like a distributive law. If you have, let's write this out briefly. If you have 3 times x minus 4 plus 6, that's not the same as 3 times x minus 4 plus 6, is it? Because this 6 has to be multiplied by 3, but this one doesn't. And similarly, you got to apply the log base 2 to the 7, but you're not going to be applying it to the 5 as you would if you put it inside the parentheses. So make sure you're clear on that. And again, I'd say just treat the log base 2 of 7 as a number. It's like a symbol. It stands for a number that we're going to be able to figure out. Okay, so then what do? We divide both sides by 3, right? So x equals log base 2 of 7 plus 5 divided by 3. Make sense? Now the question is, okay, what's log base 2 of 7? There are 2 ways you can get an approximate value of log base 2 of 7. You could make a graph of the log base 2 function, which is inverse to the graph of the 2 to the x function. Okay. Okay, so we could certainly do that, and we'd actually get a pretty good approximation. Okay, I'm saying it's going to be around 2.8 or 2.9. Because this function is inverse. Log base 2 functions inverse to y equals 2 to the x. The graph y equals 2 to the x. So you graph the inverse function. Well, normally you're not going to want to do that, but you can pretty much count on me to ask you to make estimates from a graph like this, because that's something we've been doing since the first day of class. Or at least the second day. I don't remember. Go back and look at the videos. Okay. We can do this using the calculator. How do we do it using the calculator? We use this graph. It basically just says that log base B graph is a vertical stretch of the LOG graph or of the natural log graph. And we'll talk about that a little bit more, but not right now. Okay, so log base B of C log of 7 divided by log of 2. Got a calculator handy? What's the log of 7? What's the log of 2? Log of 2 is about 0.3. Take your calculator, you've got a log key on the calculator. Do log of 2. Tell me what you got. Sorry? Somebody did something. Yeah. Let's just turn the, couldn't even tell who that was. So. Okay, quick correction. This is right. This wasn't right. I had B here and C here because I was being careless. Okay. Now it's right over here. So I just threw it down. Without that. Anyhow, it does come out log 7 over log 2. So what we want to know is you take your calculator. Okay, again. Should have been log C over log B here, fix that. But it's log 7 over log 2, which is what I wrote. And log 2 is 0.3, it's actually 0.301. Now, this is about 0.8, but there's some decimals there. It's not real close to 0.8, between 0.8 and 0.9, I think. But let's, using this approximation, log base 2 of 7 would be about 2.7. 3 goes into 8, 2 2/3 times 2.66 repeating. So it rounds off to 2.7. Now you usually want to use more decimal places here. So I'm just writing out single decimal place. So this might not be completely accurate, but my approximation That's what we get. Now, I said it'd probably be around 2.8 because I based it on the way the log function curves. In any case, that would help. And I'll show you how to do that with the graph, just so you can kind of verify things. In any case, now to do this, log base 2 of 7 is about 2.7. Add that to 5, you get 7.7. And that gives you uh, 2.8. No, 7.6. Approximately. Now you can check that. And another thing you really need to get in the habit of doing is checking your work, because that gives you instant feedback of whether you did it right. If you get that instant feedback, you learn much faster. So keep recommending that, and think people get out of the habit of doing it. It's really kind of essential if you want to learn it well. Unless you do everything perfectly the first time. The log graph, looks something like this, right? And if this is 1, and this might be 1. So if 1 is here, where's 7? Well, there's 1, 2, 3, 4, 5, 6, 7. Out about here, let's just and this one. Here's 7. Now this graph doesn't necessarily have exactly the right shape. You can always draw a log graph by drawing your just your table for your basic exponential function. Base 2 function is fine. Okay. And switch columns, sketch a graph. Then ignore your scale. 1's going to be wherever this is. If 7's out here, where's that project? If that's over to here. There's 1, there's 2, and here would be 3. Now from this graph, it looks like that's more like 2.3. So if this is your log base 2 of x graph, your estimate based on the shape I drew for this graph would be log base 2 of 7. Instead of 2.6, it looks like we get 2.3 or maybe 2.4. Okay, so I'm going to say from the graph, the log base 2 of 7 appears to be maybe 2.4. That's consistent with this result. What I mean consistent is that it's reasonable to get this estimate when the actual value is this number. And that's a reasonable estimate. It would not be consistent if this was 38. Use the graph, we've got an estimate of 38, which we wouldn't, and the actual answer is 2.6. That's not consistent at all. But in a hand sketch graph, a difference of about 10% between the two numbers means that it's likely that this number is correct. I do recommend to think in terms of graphs, but also by all means, use your calculator to get more accurate results. Use the graph to see if your results make sense. And actually, log base 2 of 7 is 2.7, not 2.6. So still reasonable estimate. Should be more like here. Is the graph scaled carefully? Not really. Okay, we're going to want to solve this equation for x. Now I'm going to put up this board here with the rules. It won't be on the screen. But this one right there. See, right there are the rules. If you're watching the video, you can pause it, write down the rules. You probably already have. We solve this using those two rules. So see what you can do. Okay. Now the kicker here is this equation is not in one of these forms. Okay. But can we put it into one of these forms? There's something we can do to that equation to put it in the form of b to the a equals c. Well, I'm going to pause for a second, see if anybody has an idea here. Okay. Well, this isn't in the form b to the a equals c. How do we put it in the form b to the a equals c? Simple enough, divide both sides by 1,000, and then you have 1.08 to the x equals whatever you get over here. Of course, what you get over here is going to be easy. So, a 1,000 times 1.08 to the x divided by 1,000, which is 4,000 divided by 1,000. That's an easy division. That's going to be 4. Of course, the 1,000 divides out, and we have 1.08 to the x equals 4. And now this is in this form. So, see what you get now. At this point, we've got a very simple equation we can translate into logarithmic form. We first identify we're in this form with a equal to x, b equal to 1.08, c equal to 4. The equivalent form is log base b of c equals a, which for the values of a, b, and c is log base 1.08 of x, of 4 equals x. Well, we don't even have to do any work to find x, just evaluate this using the second rule. So log of what's in here divided by the log of the base, which is 1.08. Okay. So now you can put that in your calculator and figure it out. See what you got. Okay, your textbook, your calculator will give you something close to 0.6 here, something close to 0.03 here. Excuse me, it's a little more than 0.03, like 0.033. But using these, just one significant figure, I get 20. So when you do it actually with your calculator, you're actually going to get something close to 18. You probably read about the rule of 72. I'll just tell you how that works. I don't have to write it down. You recognize this as your multiplier when you've got 8% interest, right? Your exponential base for 8% interest be 1.08, and x is your time. So you want to find the time that raises 1.08, the time that with 1.08 is raised to that power, gives you 4. Okay. Now 4 is convenient because it's 2 doublings. And the rule of 72 says, if you divide 72 by your percent interest, which is 8, well, you get 9. And that's the time it takes this quantity to double. Okay. So if x equals 9, this is going to pretty much give you 2. And then if you double again from 2, well, you're going to get 4, right? So this is 2 doubling times. Okay. Your money would double in 9 years, and then that would double in another 9 years, fitting that you would get the 2 doublings in 18 years. So if you want a quick explanation of the rule 72, that's it. It's not a perfect rule, but for small interest rates, it works pretty well. And that's what people use to make ballpark calculations. How much is this going to grow? How long is it going to take this investment or this population or whatever to double? If it was 4%, be 1.04 here. 72 divided by 4 is 18, so it'll take 18 years to double. And another 18 years to double again, so you'd have 36 years for your solution. And you can try that, you play around with it. It's kind of worth knowing. But I'm probably not going to test you on it. Doesn't mean it's not worth knowing though. Okay, so here's an equation that we want to translate into the logarithmic equation. So what do you get? We apply the rule for translating. Exponential equation into logarithmic equation. And I'll just tell you, you don't know what D is. Maybe you do, but look at them. Everybody doesn't, because I know a lot of you don't yet. Okay. Assume you don't know what E is. So you're just going to have to do this with a symbol E, right? Okay. Okay. To solve this, you got to put it into this form. It isn't in this form. You have something raised to a power here, but you got a number in front of it, and this form doesn't have a number in front of this. Now you can always get rid of the number in front. You just divide both sides by that number. And you very quickly get something that is in this form. Okay, B to the A equals C. Where in this case, G is just E. I'm not sure you've been introduced to that number. Because I think I went over your homework pretty thoroughly. Don't really say that. But B equals E. A equals negative 0.2t, and C equals 3. So now the logarithmic form is log of the base E of 3 equals negative 0.2t. Okay. And now you solve this for t, except you want to understand that log base E is just a natural log. Okay. Log base E is a natural log, so that's natural log of 3 equals negative 0.2t. Now you just solve for t. And I'm going to go ahead and do that for you because I think everybody gets here. That'll be good on this solution. again, move this away so the watermark doesn't interfere. We get down. If you have a decimal as a coefficient in an equation, I always recommend that you multiply by a power of 10 to get rid of the decimal so to avoid confusion. So we could write this as 10 times the natural log of 3 equals negative 2. Because when you've got decimals, it's real easy to get confused. And then we get t equals 10 times the natural log of 3 over 2, but it's negative, because you divide by negative 2. That's negative 5 times the natural log of 3. Natural log of 3 is somewhere around 1.1 or 1.2. I'm going to say this is approximately equal to negative 6. And you can use your calculator to refine that. Okay. So there's what you do if you've got an E. Now there's one more important form of exponential functions. Okay, e to negative 0.03t be written in the form b to the t. Y'all please check your masks. Okay. Be written in the form b to the t. How do you do that? You have to know your laws of exponents. If you do, you understand that e to the negative 0.03t is e to the negative 0.03 raised to the t power. And of course, when you have a power of a power, you multiply the power. E to the negative 0.03 raised to the t is e to the negative 0.03 times t. And with 0.03 times t, negative 0.03 times t is your exponent. And this is 0.97t. So the form is b to the t with v equal to 0.97. And it's very simple if you understand the rule for exponent. Okay. Now there's another thing you can write. (1.08 to the t) can be written in the form e to the kt. Okay. Since e to the kt Okay, I'm gonna pause for a minute because there's some conversation going on. I think it's about what we're doing. Okay. I say this calls for e to the k is 108, 1.08. Thousand k equals the natural log of 1.08. I'm just gonna say et cetera, since you are time y'all are ready to leave. It's fine. This open math is gonna show you how to do this. Okay.